Hello, my name is Mark Girons Lopez, and I'm a hydrologist at the Swedish Meteorological and Hydrological Institute, one of the partners in the EFAS Dissemination Center. Welcome to this new EFAS webinar, in which we will cover different aspects of how the new EFAS 4.0 can be used by end users for forecasting. More specifically, we are going to review some of the major features of EFAS 4.0 and their implications for forecasters and end users, followed by a more detailed explanation of the most relevant features for analyzing the situation, such as the revamped reporting point layer, the new static layers, and the newly added information on model performance and forecast skill. Thereafter, we are going to use some of these new features on a simple case scenario on the EFAS map viewer. Finally, we are going to talk briefly on the available data for local evaluation of EFAS forecasts and on where to find further information about EFAS 4.0. Let's start with what's new in EFAS 4.0. As you may know, EFAS 4.0, which became operational this fall, is the latest development of the European Flood Awareness System. It includes, among other, improvements in the hydrological routines of the least flood model, such as an improved channel routing, a new calibration of the model using a 6-hourly time step and stricter physical ranges for calibration parameters, corrections to the model river network, improvements in the location of river gauges on the river network, as well as updated content on new layers on the EFAS map viewer. But how do these improvements and new features benefit end users and forecasters? Let's review some of the key points. The new calibration using shorter time steps, 6-hourly, and an increased number of stations brings notable improvements for forecasters. Now, almost 50% of the EFAS domain belongs to a calibrated catchment, which means that the model is becoming better fit for an increasing portion of the EFAS domain. Following this new calibration, model performance has increased for most stations and catchments with respect to EFAS 3.5, which is the previous EFAS version. Here, you can see the cumulative distribution function of model performance for all stations for both EFAS 3.5 and EFAS 4.0, as measured by the Klein-Gupta efficiency metric. This measure explicitly evaluates three key components of the model performance: correlation, bias, and variability. A KGE value of 1 is achieved when the model fits the observations perfectly. As you can see, EFAS 4.0 efficiency values are consistently higher than those of EFAS 3.5. If we look at the spatial distribution of model performance in the figure to the right, we can see that while the model performance in EFAS 4.0 is increased with respect to EFAS 3.5 for most stations, there are some stations with lower performance values, which you can see in different shades of red here. It is actually difficult to compare EFAS 4.0 against 3.5, but the decreased performance at these locations might be due in part to the shorter periods available for calibrating the model at 6-hourly time steps. This new calibration resulted, for instance, in significant improvements on simulated flood peaks in medium-sized catchments, both in terms of magnitude and timing. Here you can see an example of the River Inn at Muhldorf in Germany, for which the estimation of both the peak timing and magnitude for EFAS 4.0 to the right are significantly better than that for EFAS 3.5 to the left. In these figures, you can also see that the discharge thresholds have changed. Indeed, new thresholds for the 1.5, 2, 5, and 20-year return periods have been recalculated based on recalibrated model climatology. Following the recalibration based on 6-hourly time steps, both for ECMWF, ENS, and COASTPOL-EPS forecasts, now also have a temporal resolution of 6 hours, as you can see in the example hydrographing here. This means that forecasts are now sharper than before, and can thus react more rapidly to new inputs and changing conditions. Statistically post-process forecasts, blending the available observations over the last 40 days, least flood water balance, and forecasts are now also available at over 1,000 stations. In here, it is important to remember that post-process forecasts might be missing if the forecast is beyond the calibration range. Last but not least, the new calibration has also led to performance improvements in the ERIC flash flood forecasts. In here, you can see how the EFAS 4.0 ERIC hit rate has increased for all lead times when compared to EFAS 3.5 for the 10% exceedance probability, which remains as the preset threshold for issuing flash flood notifications. The move to EFAS 4.0 also led to changes in many of the core forecasting layers in the EFAS map viewer, mainly due to the new model time step. Additional layers have also been created in order to help forecasters and end users take the best decisions. We are going to cover some of these changes and additions next. First, we look at the drainage network layer. The model flow paths are represented here with different colors depending on the total drainage area. As we have previously mentioned, in this development cycle there have been improvements in the model channel routing and drainage network, which will improve the representation of water flow along catchments. The drainage network layer is great to visualize all the contributing areas to a given reporting point and understand where the water comes from, as shown here in detail for Luxembourg. We next move to the least flood reservoirs and lakes layer, which is a new addition to EFAS 4.0. Why is this important? Well, EFAS has a consistently lower scale on highly regulated catchments, such in the Iberian Peninsula or northern Scandinavia. When assessing the situation, it is therefore important to know if a specific reporting point is affected by river regulation. In the example here, we can see a reporting point in pink located at river Luleälven in northern Sweden. This is a highly regulated catchment with many reservoirs, as we can see in the many green squares along the river. Forecasts at this reporting point will thus need to be taken cautiously. The reporting point layer has an important development over these past couple of years. Now, a lot of information is already displayed in the reporting points themselves, including the exceedance return period, 2-year in yellow and 5-year in red, whether the threshold is to be exceeded in the next 2 days or not, with a thick black border, etc. Exceedance probabilities for the ECM, WF, ENS, and Cosmolabs forecasts are also shown next to the reporting points when zooming in. Additionally, even if EFAS performs best for large catchments, now many more small catchments are also shown in the reporting point layer, so end users and forecasters can better monitor the evolution of discharge along catchments. Pop-up windows in the reporting point layer have now been redesigned. Discharge forecast hydrographs and post-process forecasts for those stations with real-time river discharge data available are now presented together in the pop-up windows, allowing users to easily compare the simulations and forecasts with their own observations. Hydrographs are presented for both discharge on the top row here and return period on the bottom row for the two forecast systems, so ECM WF, ENS to the left and Cosmolabs to the right. Remember that some areas of the EFAS domain are outside the Cosmolabs domain. Both systems here are now also shown at 6-hourly resolution. Scrolling down, improved figures for upstream rainfall and snowmelt and average temperature are now shown. These figures allow to diagnose what process is driving the forecast. For instance, in this case, we can see that the peak flows from the previous slide are caused by intense precipitation upstream. Finally, the persistence tables have also been reconfigured for a more intuitive reading, with the latest forecasts now on top of the figure. Notice even the 6-hourly time steps in here as well. Next, we will move to the new performance layers, which you can now find under the speedometer on the top left menu in the map viewer. The first performance layer we are going to go through is the one showing KGE model performance for EFAS catchments. As you may remember, a KGE value of 1 is achieved when the model fits the observations perfectly, so the model works best for darker color catchments in here. You can check the model performance for specific catchments you are interested in, such as, for example, the River Luleälven catchment here, which, as you may remember, is highly regulated. The model has a comparatively lower skill for this catchment compared to the neighboring catchments, which is not unexpected given the presence of several reservoirs. Model performance can also be visualized for the individual reporting points, as shown in this slide. The performance metric, KGE, and color scale are exactly the same as before, but you may use this layer instead if you are specifically looking at the individual reporting points. You may remember from before that KGE explicitly evaluates three key components of the model performance, which are correlation, bias, and variability. If you click on a specific reporting point, you will be able to see the disaggregation of KGE into these three components, in addition to monthly discharge climatology and simulated discharge for the calibration period of this station. In this example from northern Germany, both the bias and variability of the model are very good, but correlation is somewhat lower, meaning that model simulation is not perfectly linearly related with the observations. These metrics can help you put forecasts into context. For instance, if a station has a negative bias, you might expect forecasts to underestimate real values. Finally, the medium-range forecast skill layer shows the number of days forecasts have skill over 0.5 for all reporting points. A perfect skill has a value of 1, while a value of 0 indicates that the forecast has no skill with respect to the benchmark. Selecting an individual reporting point brings up a pop-up window showing both the forecast skill to the left and the scores it builds upon to the right. The score we use here is the continuous ranked probability score, which is the equivalent of the mean absolute error for probabilistic forecasts. The skill of forecasts is evaluated against a persistence benchmark forecast. In this case, the 6-hourly river discharge value persisted from the previous time step. In this case, the forecasts have relatively high skill, larger than 0.5, for the entire forecast period, so 10 days. We are now going to go through some of the features we have introduced here for a simple case scenario in the EFAS map viewer. More specifically, we will look at the recent heavy rainfall event that took place in Western Norway at the beginning of November. So, now I have opened my web browser and navigated to the EFAS map viewer webpage. And here I start with a fresh, clean map. And the forecast date in this case is the 3rd of November, 12 UTC forecast. The first thing we want to know is to visualize the probability of heavy rain in the coming 10 days. So we will go to the meteorological layers and visualize the precipitation probability for 50 and 150 millimeters for the DCMWF forecast. Now it appears, and we see that more than 50 millimeters of precipitation are very likely for the western part of Norway. And even there is some not disregardable probability that more than 150 millimeters can fall in some points. We will zoom into this part of central Norway where heavy rainfall is expected, right here, and bring forward the major rivers in EFAS. For this particular scenario, we will focus on River Namson here. We can also visualize its catchment area here on the static layers as well. You can see its catchment here, the borders, which are to a significant extent within the high precipitation area, so the 150 millimeters. We can then look at the reporting points available for this specific catchment. So we go to the flood summary, reporting points. We see that 3 reporting points are available for this specific river, 2 of them in the main channel, and both of them fulfill the criteria for high flows according to EFAS. So you see that both have over a 50% probability of overcoming the 5-year return period threshold, according to the ECMWF forecast, and have no data for the Cosmolabs forecast. This is because this river is outside the Cosmolabs domain. So we can go ahead and click on one of the reporting points to see what the forecast looks like. The first thing we see in this station is the post-process forecast, which we will disregard for the purpose of this exercise. So we will scroll down and visualize the flow hydrographs. We have both for discharge and return period here. And again, you only see the hydrographs for the ECMWF forecast, as the catchment is outside the Cosmolabs domain. In here, we can see that both the probabilistic and deterministic forecasts, they exceed the 5-year return period threshold for the days the 6th and the 7th of November. If we continue scrolling down, we can see the upstream rainfall and snowmelt, as well as the average temperature. So we see that in the last few days, there has been some precipitation over this catchment, and also some snowmelt has been occurring. This is due to the relatively high air temperatures. We can also see in here that significant precipitation is to be expected in the coming days, in addition to some limited snowmelt as well. If we scroll further down and look at the forecast persistence figures, we can focus, for instance, on the probability of the ECMWF probabilistic forecast exceeding the 5-year return period threshold. We can see that the last forecasts have all been exceeding this threshold for both the 6th and 7th of November. Nevertheless, probabilities have been oscillating quite significantly, ranging from around 25 to over 60%, which is quite a large spread. So in order to decide if we trust these forecasts or not, we want to know how reliable the model is for this reporting point, and how skillful forecasts usually are here. Additionally, we can also gather other relevant information, such as whether there are any dams along the river or not. So we'll close this pop-up window and hide the meteorological layers to unclutter the map. And we'll start by looking at the regulation. So we go to the static layers and show the least flood reservoirs and lakes layer. So here you see that, if you remember from before, reservoirs are shown with the green squares. Within the catchment we are interested in, there is only one reservoir in the least flood model. And this reservoir is located in the headwaters of the catchment. So Without any closer knowledge on the regulation volumes or routines, we can estimate that it will only have a limited impact further downstream where the reporting point is located. Okay, we can close this layer now. And let's focus on model performance. So we'll go to the speedometer here on the top left menu, and we'll start by showing model performance for the reporting points. As you can see here, not all reporting points have model performance data associated. So you might want to look for these reporting points which have performance data, or else look at the closest available performance value. We'll click here at our reporting point here. And here we see that the model has a medium-high performance based on the KGE metric. If we look at the disaggregation in these three key components we talked about, we see that correlation and variability are quite good, but the bias ratio is quite low. This means that the model would tend to underestimate the observations. This low score on the bias ratio reduces the overall KGE score as well. If we look at the monthly discharge climatology, we can see that model simulations, shown with the box plots here, tend to underestimate the observed discharge in the shaded area, especially during the winter months. This effect is, however, not so strong for the month of November, which we're currently interested in. With that in mind, we can now close this pop-up window in the model performance layer and visualize instead the skill for medium range forecasts. These are available for the same reporting points as the performance. So we'll click on our reporting point here to visualize both the forecast skill and the scores it builds upon. Here we see that the forecast skill is very high for the first lead day, but it rapidly decreases thereafter and stabilizes at around 0.6, and then slowly decreasing to below 0.5 by the end of the forecast period. For lead times up to the streamflow peak in our case scenario, so about 3 to 4 days, forecast skill is around 0.6. This means that even if forecasts tend to be significantly better than the persistence benchmark for such lead times, they are still far from perfect, which would correspond, if you remember, to a skill value of 1. Okay, so now we know how model performs for this catchment and what the skill for medium range forecasts is. So the last thing we can do for this very simple case scenario is try to gather some more relevant information that can help us understand the situation as a whole. We can do this looking at the initial conditions layer. There is a lot of information in these layers, but for the sake of simplicity in here, we will only look at the soil moisture. So we'll bring forward this layer and then drag it all the way down so that it doesn't crash with the other information. If we bring forward the legend for this layer, we see that for our catchment of interest, soil moisture is relatively low at about 0.5 for large parts of the catchment, as shown here in the yellow colors. Some smaller parts even have lower soil moisture, and some small parts somewhat higher, especially in the downstream sections here. Overall, we could say that a large part of this catchment, the soil is not saturated and might still be able to retain and absorb some water. So now we have all the possible information we could gather. And based on this information, if you remember on expected precipitation, forecasted high flow probabilities, initial conditions. This combined with the knowledge that we got on river regulation, model performance, and forecast skill, I would think that there is a medium probability that the 5-year return period threshold will be exceeded at this reporting point as a result of this heavy precipitation event. It may be also interesting to know that following the predefined criteria, a formal flood notification for this reporting point was sent by the officer on duty that day. So how good was this forecast actually? Since we're looking at the past event, let's close this soil moisture layer so we have a cleaner view. So we can go forward in time, let's say a week after that, the 9th of November, for instance, and see how the situation has changed. So here we see our reporting point that's now shown in blue, no longer in red. That means that the high flow event is already over. So if we click again on this point here, we can close this legend, sorry, and we scroll down to the forecast and observations, we can see that for the past days, the observations, the discharge observations noticeably increased. But it is also clear as well that the forecast from the 3rd of November clearly overestimated the flood peak. In any case, bear in mind that we only gave a medium probability of the stream flow exceeding this threshold anyway, so that it would overestimate the actual values was within the range of possibilities. This overestimation might be due to different factors, such as decreased precipitation with respect to the forecasted amounts, uncertainties in the hydrological forecasts, underestimation of the soil retention capacity, etc. A more accurate evaluation would be necessary to point out the specific causes, which leads me to the next part of this webinar, which is the local evaluation of EFAS forecasts. Users and forecasters have the possibility to locally evaluate forecasts, such as the case scenario we just gone through here, by retrieving EFAS forecast data. So now, in addition to the already available 30 days old EFAS real-time forecasts and the EFAS historic simulations, real-time EFAS seasonal outlooks and ECMWF-based EFAS medium-range and seasonal reforecasts are also part of the Copernicus Climate Data Store, or CDS. Users can download these datasets to conduct their own local evaluation or to use this data for downstream applications. Before closing this webinar, let me say a few words on where to find further information on EFAS 4.0. In the last annual meeting that took place on October 22nd, members of the EFAS Computational Center presented some of the key features of EFAS 4.0 to the partners. The material presented there was converted into a series of videos focusing on different aspects of EFAS 4.0. which can now be found on the EFAS website. So, for instance, if you want to know more about forecast evaluation on EFAS 4.0, you can check the dedicated video there. Additionally, you can also find detailed information on EFAS, its components and their development, including detailed information on EFAS 4.0 on the wiki page. This wiki can be accessed from a link on the top menu of the landing page of the EFAS website.